Hello and welcome to the third lecture of this module, and we have been discussing classical lamination theory for analysis of FRP laminated plate. And in classical lamination theory, some assumptions have been made in terms of the displacement field, in terms of the strain displacement relationship, in terms of the stress strain relationship, and based on those assumptions it is convenient to represent these stresses. So, it is not straightforward to relate the stresses and in the laminate, because the in layer laminate, in each layer the stresses could be different. Therefore, it is convenient to represent the stresses in terms of force and moment resultant. What is that? We will see now. Okay. So, this is what we have discussed just now, that how the strain and how from the strain we get the stresses as a how from the strain we get the stresses by okay. Now, since the stresses are discontinuous across the thickness and in each layer the stresses are different, it is convenient to actually represent these stresses in terms of force and moment resultant. Now, what is force and moment resultant? Say, what we do is we represent effect of stresses in each layer by means of stress resultant like this. Say, we write the resultant force N x as equal to, where h is the thickness of the laminate, sigma x dz. Okay. Please note that what exactly is, we have considered an n layer laminate. Suppose we have number of layers, n number of layers, say 1, 2 like this, k, there are n number of layers. Okay. And the total, this is the, say, the reference surface, and the total thickness is h by 2, h by 2. So, this is the z axis and this is x axis. Okay. And this is of course y axis. Okay. So, in each layer we have sigma x. So, we write that N x is the equivalent force, which is integration of sigma x over the thickness. Therefore, going from z going from minus h by 2 to plus h by 2. Similarly, we can write N y minus h by 2 to plus h by 2 sigma y dz, and N x y is equal to minus h by 2 plus h by 2 tau x y dz. Okay. This is, say, your equation number 9. Similarly, you can write the moment resultant m x is equal to minus h by 2 to h by 2 sigma x z dz, m y is equal to minus h by 2 to plus h by 2 sigma y z dz, and m x y minus h by 2 to plus h by 2 tau x y z dz. Okay. Okay. This is called the force resultant. and this is called the moment resultant. Please try to understand what we have done here. In each layer there are stresses. Okay. So, we have actually replaced those stresses in each layer by means of an equivalent force and an equivalent moment, which is actually acting at the mid plane. Okay. Say at each this thing, say this is sigma 1, I mean please try to understand the sigma 1 is not only sigma, it is actually all the 3 components of stresses, sigma x, sigma y. Okay. So, this is sigma 1, here it is sigma 2, like this. So, this here it is sigma n. Okay. Now, these stresses are represented by a single force. Suppose if you consider all the sigma x, the effect of all the sigma x is actually represented by a single force n x acting at the mid surface of the laminate. Okay. Similarly, effect of all the sigma y is represented by a single force n y. How did we do that? You can understand that stress at each layer multiplied by the cross sectional area gives the force. So, similarly you can take in all the layers the force, sum them up, that is nothing but okay. But in this case we have only multiplied by the thickness and not by the width. Therefore, this is force resultant, even though we are calling this as force resultant, this is actually force per unit width or force per unit length. Therefore, it is Newton per meter. Similarly, we have the shear force resultant, okay, n x y. Okay. Now, these forces in each layer or the stresses in each layer will obviously have some moment about the mid surface. So, what is that net moment? So, this is the net moment. We find out the force in each layer multiplied by its arm, its distance from the mid surface, that is the moment, and sum them up over the entire thickness, that is the net moment. So, sigma x causes this moment, similarly sigma y causes this moment m y, and tau x y causes this moment m x y. This is also the moment resultant, actually it is moment, because even though we are telling that moment of the force, but it is actually not the force, stress multiplied by the thickness, therefore, force per unit length, therefore, it is moment per unit width or length. Okay. Therefore, its unit is Newton meter per meter. Okay. Therefore, together these 6 force and moment resultant, this 6 force and moment resultant represent a statically equivalent system. Statically equivalent system of the stresses in the laminate. Okay. This is statically equivalent. Okay. Now, so we need to find out this force and moment resultant. Okay. We have expressed these stresses in terms of the force and moment resultant. Now, let us see how do we actually do this integration. Okay. Now, considering an n layer laminate, this is an n layer laminate, considering an n layer laminate, having the distance, says distances of the top and bottom surfaces of the kth layer. K could be anything between 1 to n of the kth layer as z k minus 1 and z k respectively as shown in the figure. Okay. This is how we designate the distances of the layers from the mid surface. This is the mid surface. Okay. Actually, this is the laminate, this is the y direction. We have only shown the x z. So, this is the x, this is z, and what this is the y. Okay. So, we have an n layer laminate where the distance of any layer from the mid surface is designated like this as shown in the figure. Okay. Now, the continuous integrals which we have shown, actually this 9 and 10, the continuous integral in 9 and 10 could actually be represented by the sum of the integrals of all the layers. The continuous integral, the continuous integrals 9 and 10 could be replaced by sum of the integrals of all the layers. What does it mean? It means we can write, say, suppose we take equation number 9, n x, n y, n x y we can write n x, n y, n x y, which is actually integration of minus h by 2 to h by 2 sigma x, sigma y, tau x y d z. Okay. This is equation number 9. So, this we can write as sum k going from 1 to number of layers. Okay. And for each layer we perform the integration, that means z k minus 1 to z k integration of sigma x, sigma y, tau x y for the kth layer and integrated over the thickness of this layer. So, this is equation number 11. Similarly, we could write 10 as m x, m y, m x y is equal to minus h by 2 plus h by 2 sigma x, sigma y, tau x y, z d z. Therefore, this could be replaced by summing the integral for the all the layers, for k is equal to 1 to n sigma x, sigma y, tau x y for the kth layer z d z. Okay. So, this is equation number 12. Okay. So, this 11 and 12 actually represents 6 equations. You can see that there are actually 3 in plane nx, ny, nxy and 3 moments mx, my, mxy. These 6 equations actually represents traces in the laminate. Okay. This is a statically equivalent system, stresses in the laminates. Of course, this 6 equations in 11 and 12 represents the stresses in the laminate, of course, with tau x z is equal to 0, tau y z is equal to 0, sigma z is equal to 0. That means, the transverse shear stresses are 0 and this is a good assumptions for thin laminate, which is of course, we have discussed this already. Good assumption for thin laminates. Okay. Now that the stresses are actually represented by the force and moment resultant, let us apply the stress strain relationship. Okay. Now that the we have obtained the statically equivalent system where the stresses in each layer is actually represented combinedly by means of a statically equivalent system with force and moment resultant, let us apply the stress strain relationship. Okay. Using the stress strain relations in 11 and 12. Okay. What we get is in 11 nx, ny, nxy is equal to sum of k going from 1 to n. Okay. Integration z k minus 1 to z k, this was sigma x, sigma y, tau x y dz. Okay. Now, we could actually write this stress in the kth layer, stress in plane stresses in the kth layer in terms of the strain using the constitutive relation, that means by multiplying the strain with the reduced transform stiffness for that layer. Therefore, this will be k is equal to 1 to n, okay, integration z k minus 1 to z k. So, this could be written as q 11 bar, q 12 bar, q 16 bar, q 12 bar, q 22 bar. You can only write the half triangle also because it is symmetric, but I am writing it full q 16 bar, q 26 bar, q 66 bar multiplied by, this is the reduced transform stiffness matrix for the kth layer multiplied by the in plane strains of the kth layer epsilon x, epsilon y, gamma x y for the kth layer dz. Okay. Again, the stress the in plane strain in any layer could actually, we have seen that the strains at any layer could be expressed in terms of the mid surface strains and curvature. Therefore, we can write this as k is equal to 1 to n, okay, integration zk minus 1 to zk q11 bar, q12 bar, q16 bar, q12 bar, q22 bar, q26 bar, q16 bar, q26 bar, q66 bar. Now, this strain, this for the kth layer, this strain in the kth layer could now be expressed in terms of the mid surface strains, that means epsilon x naught, epsilon y naught, gamma x y naught plus z into the curvature. We have derived this in the last class. Okay. Whole thing integration dz. Okay. Is it clear? So, this we could now break as nx, ny, nxy is equal to k is equal to 1 to n. We write the first term only, that means q bar we write the first term so sorry, this integration will be there, integration zk minus 1 to zk q bar into epsilon x naught, epsilon y naught, gamma x y naught dz. Okay. Plus the second, we just expand this now, plus k is equal to 1 to n, again integration zk minus 1 to zk q bar for the kth layer into z into, say, let me write this as first kx, ky, kxy, z dz. Okay. So, now you could see that we could express the force resultant, in plane force resultant nx, ny and nxy in terms of the mid surface strains and the curvature. Okay. Of course, along with that this is k, along with that the properties of that layer, that means the reduced transform stiffness of that layer is there. Now, this mid surface strains, now the mid surface strains and the curvature kx, ky, kxy are independent of which layer we are considering. Okay. That means, it is immaterial which lamina we are integrating or which ply we are integrating, because I am writing all these three because many times this ply, layer and lamina are used for the same meaning. Okay. So, these are independent. Also q bar k is constant for kth lamina. That means, q bar also does not vary along the thickness of that particular lamina. Why we are telling this? Therefore, we could take this q bar outside the integration, okay, and we could take this epsilon x epsilon naught, that means the mid surface strain and the curvature outside the summation sign also. Okay. Therefore, we can write n x n y n x y is equal to k is equal to 1 to n q bar matrix okay. And then integration of z k minus 1 from z k minus 1 to z k dz, and this epsilon naught is independent of layer as well as, therefore, it could be taken out, okay, plus k is equal to 1 to n. Okay. Again we can take this q matrix out, for the kth layer, integration of z integration from z k minus 1 to z k, that means, for the kth layer this is now z dz, and this curvature is independent of layer. So, this is taken out. Okay. So, we can now perform the integration, and so we can now perform the integration. This is simply integration dz and this is integration z dz. Okay. Therefore, we can now perform the integration and can write n x n y n x y is equal to k is equal to 1 to n, sorry, k is equal to 1 to n, k is equal to 1 to n q bar So, integration of z from z k minus 1 to z k is nothing but z k minus 1, okay, and then multiply by epsilon x naught, epsilon y naught, gamma x y naught. Similarly, we could also do the integration of the second part and integration z dz is nothing but z k square minus z k minus 1 square by 2. So, we are taking this half out. This is k going from 1 to n. Okay. This is again q bar matrix. Q26 bar, Q16, Q26 and Q66 multiplied by z k square minus z k minus, this is the integration, divided by 2 we have taken outside, and this is multiplied by the curvature k x, k y, k x y. Okay. So, this is your equation number 13. Okay. These are equation number 13, and we could now write this as n x n y n x y is equal to A11, A12, A16, A12, A22, A26, A16, A26, A66 into the mid surface strain epsilon x naught, epsilon y naught, gamma x y naught plus B11, B12, B16, B12, B22, B26, B16, B26, B66 into the curvature kx, ky, kxy. This is your equation number 14, where this part is actually the sum of our k going from 1 to n, q bar into z k minus 1 is replaced by A matrix, and this term sum over all the layers q bar of each layer multiplied by z k square minus k minus 1 square into half is represented by this B matrix. Okay. Similarly, where we can write where A matrix is nothing but, I am writing in short, A matrix is nothing but sum over all the layers k going from 1 to n, q bar matrix, it is actually 3 by 3 q bar into q bar k, that means for the kth layer z k minus 1. This is A, and B is half k going from 1 to n, again q bar for the kth layer multiplied by z k square minus z k minus 1 square. This is say 15, and this is, you can expand this A and B, both are 3 by 3 matrix. Okay. And like here I have shown, this is the A matrix, this is A, this is B. Okay. So, similarly, we could represent the moment resultant also. Okay. Similarly, the moment resultant could be written as could be written as mx my mxy is equal to sum over, that means this has come from equation number 10, this has come from equation number 10. Okay. This has come from equation number 12. This is, so we are referring back to equation number 12, and we can write this as sum over k going from 1 to n integration z k minus 1 to z k, okay, into sigma x sigma y tau x y z dz, and we use the stress strain relationship here, and this becomes sum over all the layers integration z k minus 1, just analogous to what we have done for the force resultant. So, here we write this as q bar for the kth layer and multiplied by the strain, okay, multiplied by the corresponding strain. So, I am just replacing that strain in the kth layer in terms of mid surface strains and curvature, we have already done, therefore, I am cutting it short, I mean I am just skipping one steps. So, this will be epsilon x naught, epsilon y naught, gamma x y naught plus z into k x, k y, k x y, and the whole thing integration z dz. Okay. So, we can write this as, therefore, mx my mxy is equal to sum over all the layers q bar q bar matrix for the kth layer q bar matrix for the kth layer. We can, I am again skipping one step because q bar could be actually taken out of the integration sign. Therefore, z k minus 1 to z k, this is z dz, okay, z dz into the mid surface strain epsilon x naught, epsilon y naught, gamma x y naught, okay, plus sum over all the layers second term k going from 1 to n, okay, q bar for the kth layer integration z k minus 1 to z k, then this is z square dz and this curvature is independent of layer. Therefore, this is k x, k y, k x y. Okay. Now, we could express the moment resultant in terms of the mid surface in plane strains and the curvature, okay, and the curvatures. Again, because I have already we discussed already that this q bar is constant for a given layer. So, within that layer it does not vary, therefore, it could be taken out of the integration sign, and these mid surface strains and curvatures are independent of layers. Okay. For a given laminate it is same, therefore, this they could be taken out of the integration and sign also. Therefore, we obtain this and then we can do the simple integration and we get m x, m y, m x y is equal to, if we do this integration z dz from z k minus 1 to z k, we get z k square minus z k 1 square, the same like this. Okay. Therefore, we do this integration and we can take this half outside. Therefore, this is q bar this q bar matrix for the kth layer multiplied by z k square minus z k minus 1 square into the mid surface strains epsilon x naught, epsilon y naught and gamma x y naught. Similarly, the second part you can see the second part, the integration is actually z square dz. So, there will be z cube by 3. So, we can write the simple integration and we can take this 1/3 outside, k sum over all the layers. Okay. This is q bar, q 11 bar, q 12 bar, q 16 bar, q 12, q 22, q 26, q 16, q 26, q 66 bar for the kth layer multiplied by z k cube minus z k minus 1 cube into the curvature k x, k y, k x y. So, this is our equation number 17. Okay. So, this could be now written as m x, m y, m x y is equal to, if you remember we have already defined the B matrix. So, this is the B matrix again. B 16, B 26, B 66 multiplied by epsilon x naught, epsilon y naught, gamma x y naught plus d 11, d 12, d 16, d 212, d 22, d 26. The symmetric matrix, but I am writing just for the sake of completeness. You could write only the upper triangle and multiplied by the curvature k x, k y, k x y, where this is the B matrix we have already defined while defining the force resultant, and this is a new one. Sum over all the layers 1/3 into q bar k z k cube minus z k minus 1 cube is the D matrix, okay, where D is sum over all the layers 1/3 q bar k into z k cube minus z k minus 1 cube. So, this is your equation number 19. So, what we could do is we could actually relate the force and moment resultant in terms of the mid surface strains and curvature. That means, for a given laminate, given the force, we can find out the mid surface strains and curvature and vice versa. Okay. So, what is this Nx, Ny, Nz, Mx, My, Nz? Suppose we have a laminate and we apply a force along x direction. So, we can find out what is this Nx, force per unit width will be the Nx, and subjected to that, what will be the response of the laminate? We could immediately find out what are the mid surface strains and curvatures. Okay. So, we will discuss in the next class the details on this, that how to correlate the forces with the mid surface strains and curvatures in terms of this A, B and D matrix. Note that this A, B and D matrix are the functions of the properties of each layer as well as the dimensions, that means the thickness, and the you can see that z k and z k minus 1 is decided by where it is located. Therefore, it is the A, B and D matrix are decided by the properties of the each layer, that means the Q matrix. Q matrix is again decided by U1 into G1 to nu1 to and theta, and its location as well as its thickness. Okay. So, we will continue in the next class. Thank you.